Good morning. So these are your notes for the start of Chapter 8. Chapter 8 is all of about 5 or 6 lessons, and it's about sequences and series and list of numbers and patterns. So we're going to kick things off by talking about the differences between sequences and series. Now, this chapter does have a few symbols in it that's going to be new for you, so you're going to have to make sure you recognize those symbols. This chapter will also have the challenge of asking you to look at a list of numbers and possibly notice a pattern between them, or a way that they are increasing, or a way that they are listed. So we want to start by understanding what is a sequence and how can we find patterns from it. So our objective is going to be that I will be able to, meaning you will be able to use sequence notation to write terms, write a rule, aka a formula, aka a function, for the nth term of a sequence, and find sums of sequences to get the series. So starting with what a sequence is. A sequence is an ordered list of numbers. The key here is that it is ordered. So we can list any set of numbers, but a sequence is ordered in the way that the first number needs to be the first number, and the second one needs to be the second one, and the third one needs to be the third one in order for the pattern to hold. So the fact that the first number, if the first number is 8, there's a reason why that's the first number. If the second number is 16, there's a reason why that's the second number. So we want to make sure we understand that with a sequence, it's a list of numbers, but they are ordered in a specific way. Now, there is such a thing as an infinite sequence, meaning it never ends and it goes on and on and on and on. But we need to understand that there's also finite sequences. And so that's what we're talking about here with finite sequences. A finite sequence is a function that has a limited number of terms. Okay, with a domain of 1 through n, where 1 through n is how many terms you have, not the value of the terms, but exactly how many of the terms you have. So a finite sequence would have n number of terms. And then the range of this function are the actual terms in the sequence. So what's the actual value of the first number? What's the actual value of the second number? What's the actual value of the nth number? So the domain is the placement or the order of the number. The range is the actual value of the term. So if we take a look at this visual representation here, our domain is our first, second, third, fourth, all the way to the nth number. And the range is the actual value of the number. So notice the notation here. Our first term is labeled A sub 1. There's a subscript of 1 to represent that this is the first number. The second number is labeled A sub 2. Subscript of 2 to notate that it's the second number. The third number is A sub 3, subscript of 3 to notate that is the third number, and so on until A sub n, n being the last term that we have, whatever that might be. So if I had 10 terms in my sequence, this would be A sub 10. If I had 50 terms in my sequence, this would be A sub 50, with n being 50. Now, we can be given a rule, aka function, aka formula, for our sequence and be asked to find the first however many terms of the sequence. So for example, we have 2 versions of the rule. One is A sub n is equal to 2 times n plus 5. So notice we have n twice here. One's to notate the actual symbol for the term and one to plug into this equation to actually get the value of the term. And similarly over here, this is more like a function notation. So we have f of n is equal to negative 3 to the n minus 1. Again, f of n being the placement of the term, and then we plug that in here to actually calculate and get the value. So these are the rules, aka formulas, aka functions. So if we take a look at our first one, a sub n is equal to 2 times n plus 5. Okay, first 6 terms is what we're looking for. So for term 1, okay, so term 1, that means that our n is equal to 1 for the first term. So our n equals 1 for our first term, which means that we just simply take 1 and we plug it in. So we're looking for a sub 1. Okay, we're looking for a sub 1 here, which means we're going to plug in 1 for n. And when we plug in 1 for n, we get 2 times 1 plus 5 is equal to 7. So our first term in our sequence is actually 7. So first term, a sub 1, is equal to a value of 7. Term 2 of the sequence means that now for term 2, our n is equal to a 2. And we do the same exact thing. We plug in 2 for n. So we have a sub 2 is equal to 2 times 2 now plus 5. 2 times 2 is 4 plus 5 is 9. So a sub 2, the second term, is equal to 9. So far our sequence goes 7, 9. Third term, we're now going to plug in n is equal to 3 because that's our third term. So now we have a sub 3 is equal to 2 times 3 plus 5. We get 11. So 7, 9, 11. Okay, and then for the fourth term, I hope you're seeing the repetitive pattern here. Our fourth term, n is equal to 4. We plug that in. A sub 4 is equal to 2 times 4 plus 5 equals 13. Similarly for term 5. Okay, fifth term, n is equal to 5. So a sub 5 is equal to 2 times 5 plus 5, which is equal to 15. So 7, 9, 11, 13, 15. And of course, the sixth term of the sequence, n equals 6. A sub 6 is equal to 2 times 6 plus 5, which equals 17. So these are the first 6 terms of our sequence that is defined by a sub n is equal to 2 times n plus 5. Similarly, over here, like I said, exactly the same thing, except it's in function notation. So for term 1, n is equal to 1. We plug in 1 for n. This is negative 3. 1 minus 1. We work it out. Negative 3 to the 0 power is 1. Second term, n is equal to 2. Same thing. Third term, n is equal to 3. Plug in 3 for n. So we have f of 3 or a sub 3 is equal to negative 3. 3 minus 1 is equal to negative 3 squared, which is 9. N to the fourth, n equals 4 for the fourth term. Okay, a sub 4 equals negative 3 to the 4 minus 1, and so on. Okay, fifth term, n is equal to 5. We plug in. Sixth term, n is equal to 6. We plug in. I would suggest pausing here so you can get this all down. But the idea is that whatever terms you go to, the n is the placement of the term, and that gets plugged into our equation to figure out the actual value of our term. So these are our domains. These are the ranges here. Okay. So once you're done copying that down, we can go on to the second example. Now this is describing a pattern, writing the next term, and writing a rule for the nth term of the sequence. So just like you saw here, for both of these cases, we're doing something to the placement of the term. So we're using the 1, the 2, the 3, the 4, the 5, the 6 within the equation. So when we take a look at a list of numbers, we want to start thinking about them as with their placements. So over here, I have negative 1, negative 8, negative 27, negative 64. And so we want to then think about, okay, so negative 1 is the first term of our sequence. Negative 8 is the second term of our sequence. Negative 27 is the third term of our sequence. Negative 64 is the fourth term of our sequence. So we start looking at adding and subtracting. Okay, if negative 1 is the first term of our sequence, is there anything that I can add or subtract to 1 to get negative 1? Well, if I do 1 minus 3, or 1 minus 2, I would get a negative 1. Okay, 1 minus 2 is a negative 1. And then you see if that pattern holds here as well. So if I do 2 minus 2, right? So we did 1 minus 2 gives us negative 1. If I did 2 minus 2, would that give me negative 8? No, that would give me 0. So adding and subtracting doesn't work. And then we look at multiplying and dividing. This is the first term, so 1, n is equal to 1 here. Second term, n is equal to 2 here. Again, we're keeping that and the placement of the term. So 1 here, if I multiply 1 by -1, I'll get -1. But then does that pattern hold here with 2? So if I do 2 times -1, do I get -8? No. If I do 3 times -1, do I get -27? No. So multiplying by -1 wouldn't work either. So I'm using the first term to try to figure out a pattern and then see if that pattern works for all the rest. Well, that kind of leaves us with an exponent. So let's try exponent now. If I do -1, or if I do 1 to the third power, that gives me +1. If I do 1 to the one to the third power, let's check this out. So 1 squared is 1, 1 cubed is 1, 1 to the fourth is 1. So let's check this out. So now let's try out 2. 2 squared is 4, 2 to the third power is 8. I need a -8, but we'll deal with that in a second. 2 to the third power is 8. So if I do 1 to the third, I get 1. If I do 2 to the third, I get 8. Let's check it out for third. 3 to the third power gives me 27. Cool. 4 to the third power gives me 64. Awesome. So the only thing that's left to check out here is the negative, because I'm getting the numbers. If I do 1 cubed, 2 cubed, 3 cubed, 4 cubed, I'm getting the 1, the 8, the 27, and the 64. So if they're all negative, then I can just kind of put a negative in the front there. So I can do 1 cubed, 2 cubed, 3 cubed, 4 cubed, and then with a negative in the front or in the inside, it would work. So let me test it out. -1 cubed, that's -1. -2 cubed, that's -8. -3 cubed, that's -27. -4 cubed, that's -64. It looks like I found a pattern. So if I do -5 cubed, then I'm going to get -125. And that would be our next term in our sequence. So then how do I write this as a pattern? Well, I have the negative and the cubed, and what's changing is the placement of the value. So the 1, the 2, the 3, the 4. So what's changing is the n, the placement of our value. So we easily replace that guy with an n, and so we have -n cubed would give us our next value, and that's our pattern right there. Okay, let's take a look at this next one. Again, if we take a look at our sequences, we see our 4 terms here. So we have 0, 2, 6, and 12. So we have our n. This is the first term, second term, third term, fourth term. And again, we start off exactly like we had here. We're seeing how is this actually going to, what pattern, what are we doing to the 1, the 2, the 3, the 4? So start off with adding and subtracting. So is there anything that I can add or subtract to 1 to get 0? Well, I can do 1 minus 1. That would give me 0. Let's test it out here. 2 minus 1 doesn't give me 2. 3 minus 1 doesn't give me 6. So I check something else out. So adding and subtracting is out. Now multiplying or dividing. Okay. There's really, if I do 1 divided by 0, that would give me undefined. 1 divided by 1 would give me 1, not 0. So I can't even find something to add, to multiply here that's like just a basic multiplication or division, really. Exponent, let's see, 1 squared does not give me 0. 1 cubed does not give me 0. Nothing really with the exponent. I can't get 1 to be 0 with an exponent. Even 2 squared is not 2. 3 squared is not 6. 4 squared is not 12. So within, what are we doing? Now this brings up something else. Okay, so we are going to have to think outside the box here. Okay, maybe we're doing something else with the n. Maybe we're not just using n as n, but we're also doing something else with the n. And so we have to pay attention, and sometimes we're going to have to use n twice here. So our first n here is our placement value. And I can start considering, what if I'm multiplying this with something else with an n?